everyone, and welcome to Caffeine to Code. Today, we are going to look into a field which is a field of leading research in computer science called machine learning, and we are going to look at an algorithm of machine learning called linear regression. It is one of the simplest algorithms in machine learning, and we are going to implement it from scratch in just a few lines of Python using NumPy as only our dependency. I will be using Jupyter notebooks for this purpose because these are handy for data demonstration and things can be carried out easily with them. So let's begin by uh, setting up our notebook for drawing beautiful graphs, for which I will use Matplotlib, and you might ignore this because this has nothing to do with our algorithm. It is just for plotting out beautiful figures. I will import Matplotlib, and then I will import the pyplot dependency as well. I cannot type very fast as it is very cold in here, and after importing these two dependencies, I will set up my plots to look more beautiful, and I will set the, what should I set, label size. Okay, axis dot label size. What should be the appropriate level size? I think it should be 14, and then I will set up the, I think it should work. Okay, that's enough. And oh my god, why it is taking so long? Okay, so it has run. Now I will create some fake data on which we will apply our algorithm. So this fake data would be generated using NumPy. So first I will have to import NumPy as np. I am generating a linear function here. I will generate first the independent variable, and for that I will be using the random function in the NumPy library. This function takes input parameter the number of rows and the number of columns. So when I'm entering 100 comma 1, it means that I want a NumPy array having 100 rows and just one column with values between 0 and 1. This one will give me values from between 0 and 1. By multiplying it with 2, I have scaled the values twice. So so the range will now become 0 to 2. And now I will input the dependent variable, which is y in our case, and since we are doing linear regression, we should try to keep our model linear. So I would write y as 4 plus 3 times x, and then generate some noise by generating some random values. Again, the array parameters will be same. Okay, so this has worked successfully. Now let's look at how our plot for these two functions looks like. This plt.plot function takes in parameters the independent variable, the dependent variable, and the type of plot which I want to plot. That is the color, the type, that is it should be dotted or it should be linear, and so on. You will see it in a second. I will need what color do I code here? Okay, let's go on with blue and dotted graph, and then I want my axis to be between 0 to 2 and 0 to 15. You will see what it means in a second. Then I will call plot.show to show my plot. Okay, so this is our data which we generated. The thing 0 to 2 means the x-axis will range from 0 to 2, and the 0 to 15 means the y-axis will range from 0 to 15 respectively. And so this is the distribution of our data. So this is our training data for the algorithm, which means that following this distribution, if we give our algorithm the dependent variable values and the independent variable values and train our algorithm on this data set, then provided a new value for x, the algorithm should be able to predict what y is. So let's begin with coding the linear regression algorithm. For this, we will be using this article, Ali Vandersky's article. A great shout out to this guy for writing such a beautiful article. So what we do in linear regression is that we define a cost function. You see here, h theta xi is the output of the actual output, and yi is the predicted output which our algorithm will predict. So this is the actual value of y, and this is the value which comes out of our algorithm, and the difference between those values gives the amount of error which our algorithm has, the inaccuracy in our algorithm, and summing that error in across all the examples will give us the average error. So this is the average error or cost. This is sometimes called the least squares cost of our algorithm, and the goal of our algorithm should be to minimize this cost so that our predictions move closer and closer to the actual values. So what we do is we have to minimize this variable, and this thing depends upon theta. Theta I will define what theta is. So what we are assuming that our function y, take this h theta x as y, is a linear combination of the inputs. For the sake of simplicity, I have used only single x1 here, single variable x1 here, but you can extend the similar approach to include n number of variables. So what we assume that our output y is a function of linear function of the dependent independent variables. Our output y is a linear function of independent variables. So now what we do is we assume this. So the only thing remains is to calculate the thetas. The thetas are the coefficients. So we want to find out the coefficients which will define the dependency. For that, we define the cost function as I said earlier. Now, this cost function is a function of theta, the coefficients. And as we have learned in elementary calculus, whenever we want to minimize a thing, we differentiate it and equate its differential to 0, and that's the point of maxima or minima. But an interesting property of this function is that it is convex, and therefore we are sure that it will have a minima when its differential is 0. So I will post a link to this article in the description, in the YouTube video description, and you must check out this article. It's a great article. So I will not go into the mathematical details, but when we differentiate, but I will just give you an overview. So when we will differentiate the cost function with respect to theta, this this expression comes out. X is the matrix of variables of the independent variable. So this, and theta is the coefficient matrix. So when we equate this to 0, what relation comes out is x transpose dot x dot theta must be equal to x transpose dot y. So what do you want to calculate is theta. So by taking the inverse of x transpose x, we can find theta in a simple equation, which is this. And this equation is called as the normal equation, and using this equation we will implement linear regression, and that is how linear regression is implemented in the machine learning libraries such as TensorFlow and scikit-learn. All of these use this normal equation for the implementation of their linear regression algorithm. So what we want to do here, we must begin by adding a bias term to our x to the matrix of independent variables. We add a bias term because any linear function has a constant term at the end, and we have not included that constant term. So we will include that constant term and define a new x with biases, and I will use the concatenate function of the NumPy library, and I will concatenate all the ones of shape 100 comma 1 to the existing variable matrix. So now I have got a 100 cross 2 matrix in which the first row is all ones, which will represent the constant term of our linear regression, and the second row is the actual variables which we got from here. Let's look at how this matrix looks like. Okay. Oh, I'm getting an error here. It is saying np1 is not defined. Okay, it should be np.ones. Okay. Data type not understood. So this must be something. Okay. I will have to pass here uh, an ordered pair, and then the function call. So I forgot the brackets here, and this should work. So this looks like our matrix. So in this, the first row contains all the ones, and the second row contains the data that we generated using the random function. Okay, so now I must remove this. So now we have the new xb. So now we will use this equation, this theta, this normal equation to calculate. I'm sorry for that. That was my just phone ringing. So this equation gives us the best theta at which the cost function is minimum. So let's name this variable theta best, and what you want to do here is that we will first calculate x transpose x, and then we will take its inverse. We'll take its inverse, and then we will multiply it with the transpose of x and again the initial output y. So let's begin step by step. First we will have to calculate the dot product of x and its transpose. So okay, so now our x is the xb, and the transpose of x, transpose of any numpy array can be accessed by the t parameter of the array, and then we have to make its dot product with itself, with xb of course. So this gives us this first term, x transpose x. Now I have to calculate its inverse. For that we will use the linear algebra function, a linear algebra inverse function from the NumPy library dot inverse. Okay, and we will include the entire expression into it, and this will give us x transpose x inverse. So we have the first term here, and now we have to do its dot product with x transpose. So it would be x transpose. Okay, I'm sorry, it's x transpose, and then we have to do its dot product with y. So that will give us the best theta. Now theta best represents the coefficients. So, and we already know the answer. What value should theta best be close to? So the constant term must be close to 4. One of the values in theta best must be 4, and the second term must be close to 3, because that's how the values depend on this. So uh, let's see what our theta best looks like. Theta best looks like, and it's pretty awesome. So our coefficient term is close to 4.5, and this is because it is accounting for this constant term 4 and this random noise that we generated. And as we know, as I've stated earlier, that this random noise is generated between generates values between 0 and 1, and the average of those values is 0.5. So this function is giving value near constant value near 4.5, and the coefficient of x is 3, and it is giving pretty damn close 2.9. It is very close to 3, and so hence our algorithm works. Now how to predict new values. So let's predict a new value with our algorithm, and that's all. We have created a machine learning algorithm from scratch, and then let's predict the new values using it. And you can use this algorithm to predict any linear function you want, and it would work the best. There might be some performance issues, but in other ways, it is a good, in fact, one of the best algorithms for linear function approximation. So now let's code new x. Let me name it x new, and let me call it np.array, and it should be let's take it 0, and okay, we'll put a comma here, and 1. Okay, so this is the array, and now I will have to add the bias term as we added earlier, np.concatenate np.once, and this time there should be no mistake. I will have to enter 2 comma 1, and this should work. Okay, not again. C class object is not callable. What the hell is this? Let me copy this thing from above here. Okay, I will copy this, I will remove this, I will paste this here, and instead I will change this thing to 2, and this to x new, and this to x new b. This should work. Oh, this worked, thank God. Let's look at the new array which was generated. Okay, great. We have 0 here, we have 1 here, and we have the constant biases term here. Now how will we predict? So to predict the values, we just have to multiply just have to multiply our best theta values to our new x. Oh, sorry, this will not give us the correct result. We will have to multiply x, because matrix multiplications are not commutative. Therefore, you have to be very careful before performing them. And then we will do the dot product, and then we will add theta best here. So this should give us y prediction, and let's see what y prediction looks like. And voila, you have your predictions. Now let us plot this new predictions and new data which we got, to see how much accurate this data is with the existing graph. So I will again plot this, plot plt dot plot, and then I will plot the independent variable, then the new predicted dependent variable. Okay, prediction, cool. And then I will give it a red color. Okay, it should look good. And then I will again set the axis to from x-axis from 0 to 2 and y-axis from 0 to 15. Okay, and then let's call plot.show. Okay, so this is our line, and wait a second, let's plot the previous graph also to see whether this line actually predicts correct values or not. So this was our x earlier, y, and let's give this a blue color as earlier, and oh, at most 2 arguments. Oh, sorry, let's PLO the plot. Okay, so this was the data which we generated using the random function, and this is our predicted line, and this is so accurate with the existing data. And that's great. You have coded a machine learning algorithm from scratch using only NumPy as our dependency, and that algorithm works so great. You can see clearly is perfect for you. So I guess that's all for this episode. Keep watching for more programming video. I'm thinking of making an entire playlist on machine learning algorithms. So to 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 keep in touch, please subscribe me, and if you like the video, share it with your friends, and do comment on the video if you need any help or if you want me to do another programming video. And that's all. Thanks a lot.